this. So I should record this bit because this is important as well. And that way anyone who couldn't make it can go back and watch these videos at their leisure, sort of deal. But yeah, there's a new item up here on the navigation bar along D2L, and that's videos. So if you click on this, it's kind of a more convenient structure of all the videos, and especially as, well, the quiz, but also the exam is coming up. This may be a good place to use to go and make sure you've watched all the videos and learned all the content. And so yeah, so kind of all in one place. And then I'll also continue, after this class period is done, I'll go ahead and add our video and all this sort of stuff as well. So this would be a convenient place to have all the videos listed. As far as other administrative announcements go, let's go ahead and hit the back button here. You have a lab due tonight, so make sure, you should have already, I remembered to hit the button to send out the pre-lab scores and all that sort of stuff, so you should have gotten those already. But yeah, the actual lab itself, if you haven't submitted that yet on D2L here, make sure you do that before the night's over. We have a quiz, so I guess I'm just skipping over a few things. You also have 11.11 web work due tonight. If you haven't finished that up, you should do that. And then we have a quiz on Friday, and exam 2 is next week. So exam 2 covers basically chapter 11. So 11.1 all the way through 11.11. It does not cover 10.1 or 10.3, the stuff that we're doing here on Wednesday and Friday. And there's kind of some historical reasons why we exclude those sections. But really, we just find it more convenient for the students to just focus on chapter 11. That's really some difficult stuff. And so, yeah, that's exam 2. I see that there's a few questions going. Any that we should discuss here, Alec?
I'm typing in answers to most of them. They're mostly about the format and stuff of the exam. You'll get more information about that later. But as for right now, as I just typed out a couple, it'll look kind of like the quiz that you already took and the one that you're going to take on Friday in terms of like how you input things. So some of them will be kind of similar to web work problems, and then there'll be some multiple choice like that. But in terms of like the exact number of how many of each, nothing yet.
Yeah, we found that there may be more multiple choice than there is in a live exam. I know before we kind of switched to the online format, we had a very formal distribution of everything. And that's great for, an online, that's great for in-person classes and in-person exams and all that sort of stuff. But what we found so far for this online stuff is that sometimes web work and kind of any of these online math programs in general, it can be quite a pain to type things in. And sometimes just a small little parentheses error or something like this, which you guys have identified greatly on, Piazza and everything, that sometimes this becomes quite a headache. And so we're trying to minimize the number of those for these more high stakes assignments like the quizzes and the exams. And so one way to get around having you type in everything is that making a few more multiple choice. And so that's why we've probably swung a little bit more towards the multiple choice. Not to punish you guys or anything like this, but just really for convenience. So that way you don't have to worry about, did I type everything in perfectly correct with the parentheses and all that sort of stuff.
And I would add too that the actual number of questions will be very similar to previous written exams. That if you look at the released exams, that the actual number of questions will be similar to that.
Yep, and so that's maybe a good segue into certainly the syllabus page and all that sort of stuff still has some great information. And so in particular for the uniform exams, of course, the time and the date and all this sort of has wildly changed, but there's this great link for practice exams. And so practice exams, we still have posted, very similar to what you did for exam 1. We have many exam 2s posted here as well, along with their solutions. So this will be a good resource. All of these problems, posted on these previous exams are meant to be done in a time setting. And that's really what you're looking for, even in web work style problems, or problems that are reasonable to be done, in 3 to 5 minutes, right? Because we have to ask so many questions and cover a certain span. And so we can't make, some of the learning set problems, they may take you a half an hour or something like this. And that's sad and annoying for that one instance, right? But it's a fine learning experience. It's not so great for the assessment stuff. And of course, you can also download on the content page, right? Because they are open notes and open book and all this sort of stuff, it still would be a good idea to download the exam 2 formula sheet and have that next to you while you're actually taking the exam. Of course, you could also have your textbook or all of your course notes and things like this, but at least here you kind of have snapshots and kind of an organization of kind of big important formulas. So I'd certainly recommend that as well. Okay, so with that, we're going to be focusing on 10.1 today. Usually the way that I start my classes is, well, after the administrative announcement stuff, I do a quick recap of the pre-class videos. And so I would like to do that here. I didn't do it last time just because it was the second 11.11 video that I had done. So I didn't feel so obligated to go through these pre-class videos. But I just want to highlight a few things that you should have taken away and kind of what is the focus of 10.1. And then we'll start on the new problems for today. So I guess maybe first off, you know, you should see that, right, the ordering is a bit wonky, that we've done chapter 11 first, and now we're going back to chapter 10. And the reason why we do this is actually twofold. The first is we found that chapter 11 usually is more difficult than chapter 10. So that should be, you know, some happiness coming your way, right? That maybe these are not as difficult concepts and stuff and problems related in, you know, in chapter 10 as they are in chapter 11. And that's, you know, on average, right? So certainly there are outliers and all this sort of stuff. But on average, chapter 10 is supposed to be easier than chapter 11. So that's maybe some good news. And the other thing is that chapter 10 kind of ties more closely into calculus 3. So a lot of the things in chapter 10 get extended upon in calculus 3, these parametric equations. That's really how you do curves in 3-dimensional space. And then we'll also be talking about polar coordinates and all this sort of stuff, and they have extensions in 3 dimensions as well. So that's kind of why the wonky ordering and why we do chapter 10 a little bit after, right? So we want more time for you guys to be able to digest chapter 11 stuff because it's more difficult. And it's nice to end on a nicer subject. And then also it leads in nicely to calculus 3, math 234. So these parameterized equations, just as an FYI, this is kind of really the way that Newton thought about curves in general. He always associated some time value. Newton was, you know, kind of a physicist and everything. And so this makes a lot of sense. And so instead of just X and Y coordinates, he imagined that there was an additional variable. Sometimes we call this a parameter, right? So this is the root of the word parameterization. So there's an additional parameter, which we call t. And again, we're thinking time when we see t. And literally, it's like you're riding a roller coaster, that you're kind of riding this curve here, and you're at different points on the curve at different times. And so this is kind of the basis for parametric equations and parametric curves. And so this section right here, you'll probably be fairly disappointed in the fact that there's very little calculus. Basically, we're learning a new algebra system here. And so when you say, hey, where are the derivatives, where are the integrals, those are coming, right? But actually 10.1 and also 10.3, we're learning new coordinate systems that you may have not seen before. And so it's very algebra heavy. It's very algebra heavy, no derivatives or integrals or things like this. We're just seeing how can we do the algebra and kind of what kind of reasonable questions can be asked as far as these parametric curves or parameterized equations here. And so there's basically 2 types of tricks that we're trying to learn how to do. And they're related with what we know and love. So the first type of trick that we're trying to do here in 10.1 is that if you're given some parameterized equations, right? So X relates with time, Y relates with time. Can you turn that into a Cartesian equation, right? Because we know a lot about Cartesian equations. These are the classic equations with just X's and Y's. And so if we can turn them into a Cartesian equation, then maybe we know what they look like. But still, we should be able to plot these things, you know, even if there's some Cartesian equations that are very, very difficult. There's some parametric equations that are very, very difficult to turn into Cartesian equations. So we'll be talking about some nice ones here. But in general, this is a very difficult problem. So we'll be doing a handful of these that are kind of selected very specifically, you know, especially in a class where we don't, you know, get calculators on quizzes and exams and things like this. There's only a few of these that you can really do by hand. So in this one right here, again, kind of going back to our days when we first were graphing equations, probably select different independent variables. So in this case, our independent variable is t, and you plug them in. And here you plug them in for both the X and the Y, and you see what points come out. And you see in this case, it ends up giving you a line. So that's the first type of equation, or the first type of trick that we're trying to learn in 10.1 is how can we take these parametric equations and turn them into Cartesian equations or just graph them on their own right. And so we do that quite a bit. We talk about, well, maybe you don't want things to go on forever. Maybe you want only a very specific time interval. So we have a specific start and end. So initial point and ending point. And we do a few more of these where, again, we're trying to turn these parametric equations into the Cartesian equations and also kind of graphing along the way. This is a great way also to help us check our answers. And then lastly, kind of the very last question that I get showcases the other type of question here, which is where you start with a Cartesian equation and you go ahead and you parameterize it. You try to turn it into a set of parametric equations. And so we talk about how there's not a unique correct answer for this. There are many correct answers, but this is kind of maybe the most straightforward way that we can turn a Cartesian equation into some parameterized equations, right? So where we have x is in term of t and y is in term of t. And so those, again, we'll see, we'll have many more examples in today's class, but those are kind of the two things that we're trying to really grasp in today's 10.1. So with that, usually I would pause here and ask my students, are there any questions about the pre-class videos or things that were a little bit unclear when you were watching those? And so I'll give you maybe 30 seconds. If you have any questions, go ahead and throw them up on the Q&A, or you can do your raised hand or whatnot, and we'd be happy to call on you. Otherwise, we'll transition and go into the new stuff. This is pretty accurate for what happens in my live classes as well. Silence, All right, well then, let's go ahead and go over the new problems here for today. So 10.1, parameterizing curves. Here again, I have a couple parametric equations, right? X relies on time, Y relies on time, or more formally, just a t variable, some other variable here, this parameter. And we'd like to plot the curve on this interval from 0 to pi. And so let's go ahead and go through this just as we did in the pre-class videos. We're going to go ahead and, just like we were first seeing Cartesian equations, we use the point plotting method, right? We plug in different values for our independent variable, in this case t, and we see what comes out for our dependent variable. But in this case, we actually have two dependent variables, right? We have x and we have y, and so it makes sense to make a bit wider of a table here and talk about x and y as dependent variables. So it looks like we're supposed to be plotting from 0 to pi. 0 to pi. And let's see, we need to sprinkle in a few more variables, right? Because a few more points, right? Because if I just choose 2, it's going to look like a straight line. So let's maybe also throw in maybe like pi over 2, that's halfway in between. Let's also do like pi over 4 and 3 pi over 4, stuff like this. So now we're going to go ahead and plug these into our x equation and our y equation and see what comes out. So if I plug in 0 into my x equation, let's see, we're going to have cosine of 0 is 1, multiply that by 2, we're going to get 2. Let's go ahead and maybe do the easy ones first. If I plug in pi over 2 into cosine, I'm going to get 0. And if I plug in pi into cosine, I'm going to get -1. Multiplied by 2 happens to be -2. Okay, if we plug in pi over 4 into cosine, this is going to be one of these like √2/2 sorts of deals. So √2/2, and don't forget we're multiplying by 2, so this is going to be √2. And then if I plug in 3 pi over 4, you have to remember if this is the plus and the minus or whatnot, but this one happens to be minus, so -√2. And you can kind of see that there's a trend that goes with the x's, right? We start off here at maybe the most positive value we can, 2. Right, because it's 2 times cosine, and then we go to the most negative value we can here at -2. Okay, now for our y values, so if I plug in 0 in for sine, I'm going to get, well, 0 times who cares, right? And likewise pi, if I plug in pi into sine, I also get 0. If I plug in pi over 2, I'm going to get 1, multiplied by -4, we get -4. If I plug in a pi over 4 or 3 pi over 4, I get √2/2. So when I multiply that by the -4 here, I'm going to get -2√2. All right, now our goal is to plot. And sometimes I've seen web work questions and even multiple choice questions on quizzes and exams and things like this, where they give you just 4 or 5 different sketches and they say which of them is, the plot of this parameterized curve right here. So this is certainly something that could be asked, in web work style, just via a multiple choice question. So let's go ahead and plot these things. So this first one, 2, 0. So something like this. And again, maybe I'll do the easy ones first. -2, 0, something like that. Maybe 0, -4. I know that one down here. Let's see. So, and just kind of an FYI, as you're doing these things, sometimes because it wants you to plot these, you need to know a few approximations here. So √2 is approximately equal to 1.4. Of course, remember, it's one of these irrational numbers. It does go on forever. And then √3 is approximately equal to 1.7. So sometimes those will come up in some of your web work questions as well. And so if you were to take now this more difficult one, we need to plot it around x equals 1.4. So somewhere along this. And y should be equal to -2 times √2. So that's going to be around -2.8-ish. So it's going to be a point right about here. And then likewise, -√2, going to be around -1.4-ish. And the height is supposed to be -2 √2. So again, that's the same value here, -2.8-ish. And so now you would just go ahead and connect these dots. And you get something like this. And by the way, this is something where, again, I really like to use the Desmos graphing system here. And so I wanted to show you before class, I did go ahead and I plotted this one on Desmos. And we'll get to kind of the final result here in just a second. But you can see I have my a values between 0 and pi. And this is a great way to graph parameterized curves in Desmos. So we just do 2 times cosine of a, -4 times sine of a, and you can choose some other variables. For whatever reason, t, it would just graph the entire thing, and that's fine as well. But I just want to show you, if I hit play here, you can see kind of at these different time values, you have a particle essentially dancing. And there's definitely some, uniformity. There's some curve that it's following. Right? And so the question then becomes, and part B of our problem here, is what curve is this point following, right? As the time changes here, and we seem to be mapping out some curve, but what is the curve that we're mapping out? And so, like I mentioned, this is part B. Give it a second, there we go. Find the corresponding Cartesian equation. So we're trying to figure out what equation, just with x's and y's, no t's or anything like this, correspond to this picture here. And so with just this picture, it kind of, there's some different ones that maybe pop into your mind, right? So it could be a parabola, it could be part of a circle or something like this. And so we don't know exactly from this. We need to go back to the actual equations themselves in order to figure out kind of what Cartesian equation would come out of this. And you may recognize that this is very similar to some of the stuff that we did in the videos. So if you know kind of right away what to do, that's great. But for this one, right, and kind of any of these, when you have sines and cosines, remember we have a great formula that relates together cosine and sine. And so it just comes from the Pythagorean Theorem. And it says that cosine squared of really anything on the inside plus sine squared, and it needs to be that same anything, so u's in this case, that if you square those right and add them together, you get 1. So in this case, we happen to have cosine of t and sine of t, right? You can notice that inside of the cosine and inside of the sine, it's the exact same thing, t. And so it will be true that we can go ahead and substitute in, and we can have cosine squared t plus sine squared t equals 1. And so from this, we can go ahead and say, well, I need to figure out what cosine squared would be equal to and what sine squared would be equal to in terms of x's and y's. And so we go back here, maybe the last time I seem to be zooming back and forth quite a bit, but notice I could go ahead and rewrite this as x divided by 2 is equal to cosine. And I could write y divided by -4 is equal to sine. So now we have what sine and cosine are in terms of x's and y's, right? So let's go ahead and back down here. Again, let me just maybe copy and paste. X divided by 2 is equal to cosine, and y divided by -4 is equal to sine. And now we're going to go ahead and plug these into our equation here. And it looks like we need to square them. So this is going to be x divided by 2 quantity squared plus y divided by -4 quantity squared is equal to 1. And if you were to go ahead and take maybe one line to simplify and just distribute that squaring that's happening everywhere, right, we'd have x squared divided by 4 plus y squared divided by 16 is equal to 1. And this is a fine place to stop, right? This is related to a circle. Notice if we just had x squared plus y squared equals 1, it would be a circle of radius 1. But those 4s and 16s are kind of stretching the circle. And so this will actually be an ellipse. And so if we go back to our picture, notice that kind of we had to move 2 out. It was kind of a circle of radius 2 in the x direction, and it was a circle of radius 4 in the y direction. So this is going to be an ellipse, a stretched circle. And so indeed, if we go back here to my Desmos graph, I have a little folder called secret, and I've just plotted here x squared over 4, y squared over 16 equaling 1. And if we hit play, we can see that kind of we have this point that's just kind of dancing back and forth along this ellipse, this stretched out circle here. Okay, so that is our first question. I think this is maybe a good time to pause and ask if there are any questions on your end, right? Any points of confusion or things that I could spend another 90 seconds talking about before we move on. All right, another perfect problem performed. All right, so let's go ahead. I know the video is focused a lot on that style of question, and so I'd like to spend a little bit more time now switching gears and going to this other style of question for a little bit, just to make sure that we really hit this up. So we're going to find a parameterization of a specified Cartesian equation. So here we have, some cubic equation. It just has x's and y's in it. And I don't want to, parameterize the entire curve. I would just like the piece of the curve that starts at this point and ends at this point. And I'm going to allow my parameterization to travel between t equals -3 to t equals 2. So that's the time values like I would like to map into this. Okay, and so for this one here, we're going to try to induce a parameterization. We're going to try to, give this t value. So our goal is to make y in terms of t, and we're going to try to make x in terms of t. That's how we're going to win the game here. And so you can try different things, but I think the simplest way to start off with these is to choose either y or x to try to be equal to t. Right? So if we're trying to make a parameterization, I think that's maybe the simplest way to start. And so what I'm going to try for this first one, usually x has been our independent variable. And so it makes a lot of sense, at least for me, to try, now that we have this new independent variable t, let's just say x is equal to t. So now I've parameterized x in terms of t. If x is equal to t, then we could go ahead and just substitute it in, right? Everywhere we see an x, we could plug in t. And now we've parameterized y in terms of t. So we see x cubed or t cubed plus 6. So this is maybe a decent thing to start with, but we have to be a little bit worried, right? So we have t ranging between -3 and 2. So the problem has already specified for us that this is the range in which t, wanders. And so we have to make sure that, does this actually match up with what our x values kind of wander between? And so if we go over here, notice that actually, so this is a good warm-up problem. That x does start at -3 and x does end at 2. And so this right here would be a fine parameterization. They happen to all very nicely line up. And so, okay, we have t ranges in this -3 to 2. And this does give us the correct points that we were interested in. And so again, with this problem, this is a bit of a strange new thing here. And so I want to kind of visualize this as well. And so before class, again, on Desmos, I went ahead and I started to graph some of this. Now it looks like it timed out a little bit. There it goes, it just refreshed. And so I have this piece of this cubic curve, right? This y equals x cubed plus 6 that I've already graphed. So you can see it's not the entire cubic, it's just kind of a piece of it. And this is the right code over here to start at -3 and end at 2. So that's just what that's specifying, is that I don't want it to graph forever. And so we tried, and so now I could go ahead and hit this secret button, and you can see, oops, keyboard came up, that for x, if I plug in my variable, my parameter, which in this case I'm using a, and for y, I do a cubed plus 6. And let's just see what happens if I hit play here. And notice that I have my a ranging between -3 and 2. It exactly parameterizes this curve. We've created a point that wanders back and forth along this curve here. So yes, this is a great way to be able to verify our answer. Okay. So of course they get more complicated, and we'll go into some of the more complicated ones down here for our example 9, but are there any questions with what we've covered so far? Okay. Well then, actually this is maybe a good point. Usually, in my classes, I like to pause and give you guys a chance to try something out on your own. And so I would like to maybe walk away for 90 seconds or so and have you try this problem if you haven't already. So we have a parameterization, we have a Cartesian curve here, and I'd like to find a parameterization, and I'm making it a little bit more difficult on you. So first of all, I'd like to find a parameterization where we have t ranges between -3 and 2. So it's very similar to our last one. And then I also have a parameterization where we just go from 0 to 1. So let's go ahead and pause for 90 seconds. Actually, this would be a good time. I'm going to refill my water really quick. Please try this problem, and we'll come back and do it. All right, so let's go ahead and start going over this one together here. This is a bit strange, right? Because I have x minus 6 equals y cubed. Again, we're still trying to find an x equation and a y equation that have t's in it in order to parameterize this. And so if we were to follow just very straightforward kind of what I came up with last time, I would try x is equal to t maybe to start with. And y then, well, if we plug this in, we'd have t minus 6 is equal to y cubed. And so if I wanted to solve for y, we would just take the cube root. So we take the cube root, and so cube root of t minus 6 here. And we can see that this is a parameterization for the curve, but we have to worry a little bit about our starting point and ending point. Right, so if I plugged in the t value of -3 into this, so t equals -3, notice that we're supposed to start off at x is equal to -21. So this doesn't exactly line up with just x equals t. And likewise, when I plug in 2, I'm supposed to be at my ending point, right? And so in this case, we would see, well, with x equaling t, we end up with 14, which, right, we're plugging in 2 and we're supposed to have 14. So, okay, things are off by a little bit here. And so kind of what I taught you in this last problem doesn't exactly work for this one, right? We need something a little bit different here. And so I would like to maybe have you guys, if anyone figured out how can we change this up in order to actually make it work, if you would please raise your hand, maybe we could call on someone to say, how did you get this to work out for you? All right, we have a brave soul. So I'm going to go ahead and click allow you to talk. And if you would please, what did you do in order to come up with this, Kate?
I set y equal to t because the two y values lined up with the t values.
Ah, so you noticed here that -3 matched up with -3 and 2 matched up with 2. And so instead of having x equaling t, if you do y equals t, maybe that's a better place to start. So yes, I agree with you completely. That will be a good way that we can solve for A here. So I'm going to go ahead and mute you. Thank you very much. Let's see, I'll disable your talking again. Okay, so if we let y equaling t, because these seem to line up exactly correctly, let's see, then we need to resolve for our other variable here. So this is all scratch work then. So if I let y equal t, then I'd have x minus 6 is equal to t cubed. And so we get x is equal to t cubed plus 6. So now I have a parameterization, x and y, relating with t. And notice that when I plug in -3 into our t variable, we do get y equals -3. So that works out well. But maybe we should be, last time I wasn't maybe paranoid enough, right? Let's see if we get out -21 for x. So if I plug in -3 in for x, so -3 cubed, that's going to be -27 plus 6, that's going to be -21. So yes, that also works out. And likewise, if you plug in t equals 2, we can see that we get out x equals 14. So that works out well as well. So that's a great trick for this case here. But what about for B, right? Because for B, sadly, we don't see a 0 or a 1. So I mean, we have the exact same prompt. We have a parameterization for this curve. It starts at this point, -21, -3, and it ends at 14.2. But now our t variable only ranges from 0 to 1, and that doesn't match up with anything. And so I guess I will pause for a second or so and see if anyone came up. So I'll just say this is A, I'll highlight this and call that good. Was anyone able to solve B or get a reasonable answer, or a good guess for B that would be willing to be called on and talk? Maybe we didn't give enough time either. All right. So yeah, this is a tricky one for the first time that you see it. So what we need to do is that I like this. In general, what we've done here is that we have y is a linear function of t, right? Another way to write this is that we've just done y equals 1t plus 0 here. And it's the simplest linear equation that's out there. And so I would like to do something similar here for trying to come up with a linear equation. But now I need that when I plug in 0 in for t, I need to come up with the y value of -3. So when I plug in 0 for t, I need to get out -3 for y. So let me go ahead. Let's start with the kind of the most arbitrary linear equation, like an mx plus b. But remember here, our variable isn't really x here. And so it's probably better to say mt plus b. So this is kind of an arbitrary linear equation, and I need that when I plug in 0 for t, so when t equals 0, I need to get y is equal to, what was it again? -3. So if I plug in 0 for t, notice that times any m, I'm just going to get 0, plus b is equal to -3. So this tells me that my b value here should be equal to -3. And then my other point, right, is when t is equal to 1. And when t is equal to 1, I'm supposed to be getting y is equal to 2, I believe. Let me just double check. Yep, so I'm supposed to be getting y is equal to 2 when I plug in my ending time, because that's where I'd like to end as far as my y goes. And so now let's go ahead. I have, again, y, which is 2, equals m times t, which is 1, plus b, which I found is -3. So with this, we can figure out our slope. So we can go ahead and maybe rearrange, and we get what? 5 is equal to m. So a good linear equation to try would be y is equal to 5t minus 3. And double check, if you plug in 0, you get out -3. And if you plug in 1, you get out 2. So this is a good parameterization for y, right? Because it matches up these t values and y values. And so now the question is, well, how do we match up those x values as well? And so we're just going to go back to our equation that we have. Now that we know what y is, we can just input it everywhere we see a y. And this is, we've done the majority of the work here. So we have x minus 6 is equal to y cubed. And remember, y was 5t minus 3. And so we can just write x is equal to 6 plus 5t minus 3. And right, if you're paranoid, it's good to be a decent level of paranoid anyway. If you plug in 0 for t, and if you plug in 1 for t, you do verify that you get those correct ending points there. And so you do get out x is equal to -21 and x is equal to 14. So this is kind of the worst case scenario here, that if you have something where kind of neither of your endpoints work out so well, they don't really match up with either your x or your y variable, you should do kind of a linear parameterization. Sometimes this is called an affine function, which I'm not sure if it still appears in WebWork, that word there, affine, but yeah, so just basically you want to come up with a linearization here, some mt plus b. But still, I think I'll have one box here just to finish up, and then maybe we'll open it up and see if there are any questions, right? And so this box here, if you have a Cartesian curve that you're trying to parameterize, right? And let's suppose that you have it in the form where you have some y equals, or it's very easy to get a y equals, some function of x. Then, in that case, I think trying to use x is equal to t, or really the kind of extended version would be using some linear equation. So let me go ahead and say x is equal to mt plus b in the worst case scenarios, and then solve for y in terms of t, right? Or likewise, if you can solve, x equals some function of y, then you can go ahead and use y is equal to some linear function with t's, mt plus b, and then you could use that to solve for x. So this is basically the situation that we were just in. Notice that it was very easy to solve x equals in terms of y's. So we were able to get x equals some functions with y's in it. And so that's why we kind of latched on to this almost is like a independent variable with y. And so we took our independent variable and we said, well, we want to match that to our new independent variable. And our new independent variable, the thing that we're doing today is parameterization, right? And so we have this new parameter t, and so we'd like to map our old independent variable to our new one here with t's, and let's try to do this linearly. Once we have that, so we got y equals 5t minus 3, we can take that and plug it in right into our x equation. And so our x equation was 6 plus whatever y was. And so that's what I mean by here at this end, right? Then you can just solve for x in terms of t, right? You can just plug it in and it becomes very nice. So this right here is a good rule of thumb I found, right? Whenever you have a y equals equation, and you have a bunch of x's on the other side, or if you have an x equals equation with a bunch of y's on the other side, this trick works. Okay, so with that, how are the questions going, Alec?
No new ones came in during that. I'll just add that you mentioned the term affine function. Well, we did used to use that, but I just looked. This one right here is very similar to web work number 12, and
Okay.
we do not use the term affine anymore. It just says your parameterization should be a linear function of t. So we did not use the term affine anymore, but it's the same thing.
Yep. So yeah, I remember a few years ago it mentioned this, but
Yep.
I think that's kind of an older term, right?
Right.
Yeah. Probably linear is just as good.
Yep.
Okay. Well, with that then, why don't we go ahead and again, kind of what I've been doing here a bunch is giving you a situation, right? And then kind of telling you how to upgrade it here. And so here's one. I have a curve where notice no matter how hard you try, perhaps, it's quite annoying to get this in terms of x equals or y equals. So for instance, kind of the first thing that I would try, I just gave you a great rule of thumb that says if you have x equals something with a bunch of y's, or if you have y equals something with a bunch of x's, right, we can solve this sort of problem. And now I'm giving you something that sadly that rule of thumb does not apply to. Because if you were to try to take this, and you know, kind of from all of our algebra stuff, I would probably try to solve this for y, right? From all of our algebra stuff, if we start to try to solve this for y, so let's maybe go ahead and subtract over x squared, and maybe let's take the square root. Notice in order to get the entire curve, you have to have the positive square root and you have to have the negative square root. And in fact, this function or this equation is simple enough, right, that we know and love it as a circle. So basically this is a circle of radius 1. And if you just include the positive square root, then you get the top half of the circle here. And if you just include the negative square root, you get the bottom half of the circle. But we want to come up with a parameterization for the entire circle. And so if you try to solve this y equals, and you just parameterize, you know, either the positive square root or the negative square root, you're only parameterizing half of the circle. And so while this rule of thumb is great for when you can solve x equals or y equals, it will not solve every possible case that's out there. And this is kind of a quick, you know, counterexample, something where you need to choose some other parameterization in order to solve this. And so I think this is maybe a good point. Does anyone have any ideas for us? Things that we could use that when squared and summed together equal 1? So again, if you have any brave students who are willing to raise their hand and give us an idea, otherwise I'll spoil the surprise here in 30 seconds.
Hey, you got one?
All right. So Jared, let's see. What's your idea? How could we possibly do this without solving x equals or y equals?
Sines and cosines.
Sines and cosines. Yeah, it's good to hear your voice too, Jared. I remember you used to sit in the front, right?
Yeah.
Yeah. All right. So yeah, sines and cosines. I agree. Sines and cosines are the right idea. And so this is kind of, basically, it's just a question that we had slightly in reverse here. So we had something like this, where we had a parameterization, and notice it has sines and cosines in it. And it turned out to not be exactly a circle, but a stretched out circle, right? And again, the radius in the x direction was 2, and the radius in the y direction was 4. So this is kind of the ellipse. And so basically what we want to do is this, but backwards, right? And so we have some stuff here that when you square them and sum them together, that hopefully it gives out 1. And so yes, I completely agree. If you try x equals maybe cosine, and you try y is equal to sine, then notice that they satisfy this equation here. You have now parameterized this curve, and when you take cosine and you square it, plus sine and you square it, so x squared plus y squared here, well, we know that from the Pythagorean theorem that this just equals 1. So this seems to be doing a good job, but notice that there's some extra conditions here. So we'd like to start at 0, 1 and end at -1, 0, and we'd like to travel in the clockwise direction. So notice that, well, when you're doing a parameterization and we want only a piece here, maybe we could go ahead and specify a t range, right? So the normal t range for cosines and sines would be from 0 to 2 pi. So if I wanted to parameterize the entire equation, right, or the entire circle here, maybe going from 0 to 2 pi would make a lot of sense. We should also check which direction we'd be heading in, right? So if you plugged in bigger and bigger t values as you go from 0 to 2 pi, right, you're going to actually be going counterclockwise around the circle, which makes a lot of sense. That's typically how these things are done. So we'd like to start at 0, 1 and end at -1, 0. So I would like to, maybe I'll draw another circle down here. Start at the north pole of the circle, 0, 1, end at -1, 0. So -1, 0 is over here. So I'd like only this piece right here. I don't know why I used red. Usually I use red when things aren't going quite correctly. I'll use green. And we'd like to do this in the clockwise direction. So I'd like to be going in this direction here. So, okay. So I guess notice maybe one kind of trick that you could maybe start with is saying, well, let's just have t range from pi to, let's see, 5 pi over 2, for instance. So if we have t equaling pi, and remember t is essentially taking the place of theta here nowadays. So if we plug in pi, we do have the good starting point. So that would be at t equals pi, or theta equals pi. But then if we go to 5 pi over 2, 5 pi over 2, that's going to be, again, kind of here's 3 pi over 2, 4 pi over 2, 5 pi over 2. We get to our good ending point, but we took the long way around, right? And we went counterclockwise rather than clockwise. And so we need to come up with a slightly kind of different idea in order to come up with how do we go clockwise. And so there's a couple of different ways that we can go about this. I would say maybe the simplest way, and I don't know, I've never really talked to other instructors about this. So maybe Alec, you can just yell at me and say, this is absurd. But I don't mind running time backwards, right? So this is just a variable here. And so if we start at, t equals pi, and if I run time backwards and I go to t equals pi over 2, I have no problem with that personally. How do you feel about that, Alec?
I usually don't use negative time, but I'm not going to call you crazy. I have a question though. If you're, it's specified we're supposed to start at 0, 1, right?
Yep.
And end at -1, 0.
Sorry. And and it said go clockwise. Oh,
and it said go clockwise. So don't we want that purple part then?
Yeah, thank you.
Instead of the green. Yep.
Well, I'm crazy for a different reason then. So yeah, sorry, I mixed up. I just saw clockwise and I thought I threw the first bit completely out the window. So yeah, we want to start at 0, 1 and we want to end at -1, 0 going clockwise. So let's see, I want to go this way around. All right, so sorry about that. It's wrong for a couple reasons, guys. And so we need to, I guess I need to go back to the drawing board a little bit. Still, we could use these kind of similar ideas here. So there are other ways, right? Instead of using maybe x equals cosine and y equals sine, right? No one said that x has to be cosine and y has to be sine. And so one thing that you could say is, well, what if we were to flip these things? So this is one idea maybe. So what if I did x is equal to sine and I did y is equal to cosine? Then notice that this will still parameterize the exact same curve here, because when I plug them in, x squared would be now the sine squared bit, and cosine squared, add those together, you get the 1. So now let's see, maybe where are we? This is maybe a little bit different. If I plug in t equals 0, because it's not at all intuitive what I've done here. right? Sure, it's still on the same curve, but it's kind of hard to see kind of where we are for our starting point, which direction we're traveling, all of this sort of stuff. So now think back to kind of back at the beginning of the video, we were going to plug in different time values and see where we are as far as x and y goes. So we could also just make a little table here. So if I plugged in t equals 0, notice that I start off, well, sine of 0 here is going to be 0, and cosine of 0 is going to be 1. So, okay, well, actually, that's pretty good, right? Because we wanted to start at 0, 1. Let's maybe get an idea for which direction we're traveling just by plugging in a bigger time value. So, I mean, I think the next nicest one probably is around like pi over 2. If you're happy with pi over 6 or anything like this, you can certainly plug that in as well. So if I plug in pi over 2 into now my new x, so we'd have x is sine of pi over 2 is going to be 1. Cosine of pi over 2 is going to be 0. So notice we've started up here. Again, I went back to my red pen. So we've started up here at 0, 1. And at pi over 2, we've gone to this point here, 1, 0. So it looks like this has actually gotten us by swapping these. Instead of going counterclockwise, we're now going clockwise. And as we continue, right, notice that we're not at a good ending point yet. We want to end over here still. But now you could probably guess that I think that we're going to end maybe if we go to 3 pi over 2. So let's go ahead and verify this. And of course, you could go ahead and interject as well, t equals pi. But let's go ahead, if we plug in 3 pi over 2 into x, which is sine, what sine of 3 pi over 2 is going to be -1. Y, cosine of 3 pi over 2 is going to be 0. So notice we do end at -1, 0. So therefore, if we let t range between 0 and 3 pi over 2, we get exactly the piece of the circle that we want. So this right here is the parameterization. We have to specify what are the equations for x and for y. And again, if you let this go on forever, right, you would get the entire circle. So in order to get only the piece that we want, we go ahead and restrict our time. Say we're only going to look when t ranges from 0 to 3 pi over 2. All right, so this is probably one of the most complicated ones here. I'm sure there are some questions. Anyone have any questions that you want to type out, or you can raise your hand and we can call on you, or how are you feeling? Going once, going twice. All right, so you can see with these kind of in general, you have to do a little bit of guessing and checking, right? Kind of have a good rule of thumb for this back here. Certainly using sines and cosines is along the right path for this, but then in order to make sure that you're going in the correct direction, and in order to make sure that you start and end at the right point, it's a decent amount of guessing and checking. See, there's a few questions. What do you see, Alec?
Let's see, so what are the tips for these problems is the first question here. And then, is that a common method of reversing direction, simply switching which variable is assigned, at least in the trig cases?
Would you like to take those, or would you like me to?
Yeah, I guess that's fine. If you need to point at anything on the screen, you can take over. But yeah, I mean the tip of guessing and checking, I think we say in general the tips for these problems. Yeah, guessing and checking is definitely a good way to do it. And it is a fairly common way of reversing direction to switch the cosine and the sine. And there is the possibility of running the time interval backward as well. If you had not switched the cosine and the sine, you could have done it running the time interval backward and get the same result.
Yeah, so it's a little bit, so again, t kind of, we think of it as time, but it's not formally time. You can, parameterize these things. And just like you can take the integral, from 0 to pi, you can also take the integral from pi to 0. And, that makes completely fine math sense, right? So you can kind of run things backwards, and we've seen it in integrals and other calculus style problems. And so that's why I'm not so perturbed by it, I guess.
Yeah, and I mean, in the sense that you can also think in this particular problem, you can think of t as just standing for theta, think of it as an angle. And
Yeah.
then it makes perfect sense to just let the angle start at, say, pi over 2 and end up at, say, negative pi, and run the angle in that direction. That's not really a problem.
So yeah, I'll say there's kind of some other ways that you can switch directions. So if you find out that your parameterization is going in the wrong direction, so certainly swapping the x's and the y's here, and this will, I want to be very clear, this works with the sines and the cosines. Kind of if you have any old parameterization, this isn't going to work. But for the sines and the cosines, the trig stuff, yes, it will work. The other thing that we could have done is that I could have, I started off with x equals cosine and y equals sine. Notice that if you induce a negative sign into one of these, so if I have negative cosine of t, notice that when you square those, right, when you square the x and you square the y, the negative sign doesn't super matter. And so you are going to parameterize the same curve. But now what you find out is, before you would be going from maybe 0 all the way up to 1, but now you're going to be going 0 down to like -1 or something like this, right? So kind of, it will have the effect of switching your directions. And so likewise, you could have chosen to choose the negative sign here. And so you have cosine and negative sign. That would have also got you going in this other direction. You have to be careful, of course, if you apply 2 negative signs, you'll undo yourself and you'll end up going in the same direction. So those are some other kind of tips. If you wanted to switch directions and you have like a circle and an ellipse or something like this, or even a part of one, these are some ways that you can switch directions. All right, so with that, maybe we'll look at our last problem or so. I think this is, I have more here. Let's see, what time is it? So yeah, we're getting pretty close to the end. So this will probably be the last problem that I go ahead and videotape, since it is getting close to 3 and I want to be respectful of people's time. But I'll do the other problem and I'll go ahead and post the notes on that as well. And so, okay, example 11, notice that I have a different parameterization or a different parameter here. Instead of using t's, we've used thetas, which again, kind of in our last one, we just used t's instead of thetas. Here, we're using thetas instead of t's. But the question is, I have a couple of different parameterizations. Which of them could make this graph here? And so I've done this out on Desmos ahead of time, and I've plotted it here, and we want to see kind of which of these could make this. And so my strategy for this type of problem is to just go ahead and start plugging in different values for my parameter. So in this case, my parameter is theta. So if I go ahead and I plug in, for instance, theta equals 0, or this is equivalent to plugging in t equals 0, and I just want to know what point I would get out. And so I'm going to do that for A, and for B, and for C, and for D. And I want to know, again, I'm trying to make this curve here. If I get any points out that aren't on this curve, well, there's no way then that this could be the parameterization. And so, okay, if I plug in theta equals 0 to my first one, I would get 4, comma, and if I plug in 0 here, I get 0. So I get 4, 0. So let's go over here and plot 4, 0. 4, 0 would be way over here somewhere. So there's no way that it could possibly be A, right, because the outputs aren't on this curve. So, okay, A is out. How about if I plug in theta equals 0 into B? So again, I'm going to get cosine of 0 is 1, and when I cube that, I get 1. If I plug in theta equals 0 for my y function for B, I'm going to get 2 times 0 cubed. Well, anything times 0 is going to be 0, so I get 1, 0. So 1, 0 is on this curve here, so I can't rule out B yet. So B still seems like a good candidate. How about if I do C? Again, I'm plugging in theta equals 0 into all of these things. And so I'm going to get what cosine of 0 is 1 plus 0 times who cares, right? We're just going to get 0 there. So it's going to be 1 plus 0 equals 1. For the second, right, for the y equation, if I plugged in theta equals 0, well, sine of 0 is going to be 0. And then again, theta is equal to 0. And so 0 times anything, 0. So 1, 0. We already saw 1, 0 is on the curve. So that's a perfectly fine guess here. And then, okay, here we have something a little bit more complicated, right? We have cotangent. So we need to remember cotangent, that's going to be cosine divided by sine. And so if I plug in theta equals 0 into this, theta equals 0, well, this is going to be 4 over 0. And so this is going to be infinite, right? Dividing by 0, this is going to be one of those infinite solutions. That's not on the curve. Notice that all of these are very finite, right? X does not go off to infinity at all. And so, okay, D is also out. And we could even check, right, if we plug this into, for our Y equation, it would be infinite kind of going off along the X axis here. Okay, so now we're between B and C, and we can just play this game a few more times. Soon we'll find a difference. So if I go ahead and I try maybe theta equals pi over 2, that's another thing that we could plug in. So if I plug in theta equals pi over 2 for B and for C, so let's see, for B we would have cosine of pi over 2, that's going to be 0. Cube that, we're going to get 0. And then let's see, sine of pi over 2 is going to be 1. Cube 1, we get 1 times 2 is going to be 2. So 0, 2. All right, nothing wrong with that. That seems completely reasonable. And if we plug this in for C, so C, we're going to have cosine of pi over 2. That's going to be, so again, I'm looking right here. Cosine of pi over 2, we're going to have 0 plus pi over 2, and sine of pi over 2 is going to be 1. So for our X value, we're going to have pi over 2. For our Y value, plugging it in here, we're going to have sine of pi over 2. So sine of pi over 2, that's going to be 1 minus pi over 2, and cosine of pi over 2 is going to be 0. So this is going to be equal to 1. So pi over 2 comma 1. So pi over 2, remember, this is around like 1.5 or so. Pi over 2 is around 1.5, a little bit larger than that. And then the Y value was 1. So this one is not on the curve. So the correct answer in this case is B. So again, this is a completely reasonable type of question that you could be asked on homework or quizzes or exams or anything like this. Okay, so yeah, well, we'll stick around for another 5 minutes or so if there are any questions, but otherwise we're at 3 o'clock. Again, there were a few questions that I didn't get to, and this is very typical for my classes as well. And so you should try these ones on your own, and then I'll go ahead and post the solutions here a little bit later today. But in the meantime, right, we'll stick around for another 5 minutes if there are any questions. Are there office hours after this? So I have a meeting with a one-on-one meeting with a student that I promised after this. Right now, my office hours personally are by appointment because I kind of repurposed. Remember, my office hours were during this time right here, and I've repurposed this to try to do some live lessons. And so right now, all of my office hours are by appointment. If there ends up, before when I was doing office hours, I'd get, you know, maybe 1, maybe 2 people at most. And so that's kind of why I've gone the by appointment route. So I don't have any office hours, open office hours directly after this, I'm sorry.
Just remind everybody that the MLC is open today. You can do it through Zoom. Just go to the MLC webpage and get questions answered there. You can also, of course, post your questions on Piazza.
All right, so I see a few questions here. How many points is lab 6 worth? All right, so lab 6 should be worth 20 points, the same amount as any of the other labs. Will be supplied the graphs on problems like this last one. So yeah, I mean, if we wanted to ask a style question like this on the homework or the quiz or the exam or anything like that, yes, we would supply the graph. I think this one would be a little bit crazy to, you know, graph by hand, personally. So a lot of those that you're graphing by hand are relatively nice. Circles, lines, parabolas, things like this. Any of them that are too crazy like this, yeah, we give you a graph and say, you know, something like this question where we say, you know, which of them could parameterize this curve?
I see a question here that said, why did you test theta as pi over 2 in the last example? And for that, you know, you don't have to use pi over 2, but it's a nice convenient value. So if you, first of all, if you look at the graph, you can really tell exactly where the points are on all the axes, right? So that's it. With theta would be 0, or possibly at pi over 2, or pi or 3 pi over 2. And then you kind of land right on those values. But you could have, instead of pi over 2, you could have tried pi and see if you see any difference there. You could have tried 3 pi over 2. You could even have tried something like pi over 4 or pi over 6, but then you'd be estimating a little with the decimals.
Yeah, exactly. Right. And that's kind of what we've been doing for a lot of these here, is that notice that I've stuck pretty close actually to 0, pi over 2, pi, 3 pi over 2, 2 pi, unless if there's a compelling reason why I'm not getting, if I couldn't tell the difference between these at all and I plugged in all 4 of those, which again, then it's probably not making a very good quiz or exam question at that point. But if I had plugged in all of those and I couldn't tell the difference between those two, then I'd maybe begrudgingly start plugging in pi over 6 or pi over 3 or things like this. But yeah, usually those kind of nice one at the poles kind of are the ones that I start with. I also see a question here, where can I get help for lab 6? So right now, Piazza is the place to go for help on the labs. I've actually been kind of surprised, because you're allowed to talk to each other and all this sort of stuff. We should start also maybe a list of people who want to work together. There's no reason, you guys can host Zoom meetings and all this sort of stuff that you could get together with, 4 or 5 other students, and someone could share their screen just like this and kind of run through the labs and kind of have it more in line with what the labs used to be before we kind of split up like this. So there's no reason that you can't do that. And maybe certainly for the lab practicum or something like this, I can suggest this to the supervisor of trying to get at least some names of people who are interested in working together, and then it'll be up to you guys to decide when you want to meet and all this sort of stuff. So that's my answer for where you can get help for lab 6. What's the final answer to example 8? Oh, this is the final answer to example 8. Sorry, I can highlight it or whatnot, but this does it. This parametrizes the curve. Like I said, it's a good warm-up problem. It's a good one to kind of get into this, but we saw that we extended this quite a bit. Similar question about example 8. What is the final answer we would expect to have on web work / the exam? Many times when I see this on web work, they specify for you this range here, and they also say that one of your variables should be linear. And so this would be a fine thing. So they'd probably specify again for you these t ranges, so you don't get to really choose that so much. And then you have a box for x equals, you have a box for y equals, and you just plug those things in. All right, I think that's all of the questions that I see here.
There was one back, it said that if we have a problem like example 10, what is a good way to save time on the problem? And I would say, yeah, there it is right there, that again, it's a lot of trial and error, but things to save time, certainly use values that are easy to calculate, like 0 and pi over 2 and pi. Try those first. If you have to fill in more details, you can always go to a pi over 6 or something, but try the easy values first. And then for changing directions, again, switching the x and y often works, or those two things written over there where you can just try putting a negative in front of one of them. So stick with simple values. Try just changing a sign if you need to go the other way around the circle, and see if that does it.
Yeah, and these are one of the questions too that maybe when you first encounter them, and with the explanation and everything, it takes a while. But when you try 5 of them or so, on your own with the web work homework and maybe the assessments and stuff like this, by the time you get to the quiz and the exam, you'll be doing them much faster, first of all. And then second of all, we saw, right, that this one did take quite a bit of time, right? And that there are so many actual correct answers. We go and I could, probably write down 10 different correct answers that don't look, exactly like the answer that we came up with. And so there are so many correct answers in this case that it actually may be better to style the problem like this one here, right? Where you have some picture, or we could even just give the equation, right? So rather than the picture, we could come up with the equation like, x squared plus y squared equals 1, like we did on the last one here. And we could say, which of the following parameterize this from 0, 1 to -1, 0. And we could give a whole list of things out including the time range and stuff like this. So that would be another way that we could go, where then it wouldn't, you know, you don't have to be as creative with those style problems. You just have to kind of plug in values and kind of eliminate some of them. Okay, well, I think that's it. Thank you so much, guys, for coming. Again, I'll go ahead and finish up these last examples and I'll post them online. If you have any questions, feel free to post them on Piazza and stuff like this, or reach out via email. I'd be certainly willing to help out. Otherwise, right, don't forget about the lab that's due tonight. Quiz on Friday, and then we'll also do our 10.3 lesson, the first part of it anyway, where we'll be talking about polar curves. All right, thanks again, guys. See you later.